Welcome back. This is video 2. It will be shorter than video 1. All right, so we're still in section 4.9. Video 1, you should definitely watch first. It's talking about computing antiderivatives, which is essentially the opposite of computing derivatives, right? So you start with a function and say, well, whose derivative is this function? So in this video, we'll talk about some differential equations and a comment on linear motion. All right, so we'll start with the definition of a differential equation. You can see I have my problem pre-written out. Don't worry about that just yet. Fix my lighting. Okay, so in a differential equation that we'll deal with in this class, it's a much bigger topic that is its own class, but what we'll be doing is we're going to be given information about a derivative. So they're going to give us f prime and some extra piece of information. So it's actually an initial value problem. So they give us the derivative and some point on the original function. It's possible they'll give you other information instead of that, but this is kind of the standard setup. And then using that information, you're asked to find a formula for the function f of x. So the idea is like it's a combination of antiderivative plus a little bit more, because if you can compute an antiderivative from the formula, and then if they tell you a point that's on the function, you can use that xy point to solve for the value of c. So you don't have like the general like plus c at the end, you have like plus an exact number that makes it fit the information. So it's sort of an extra step on what we've been doing. All right, so my example is already written out here. In these, they very often use the derivative notation. So here you can see they gave us f prime and are asking for regular f. You may also see this, that they say the derivative is just little f, in which case they would use big F notation down here. All right, so we want to find a function, find a formula f of x, where the derivative is this stuff here, and then also f of 0 is -2. So we're going to start by finding the general antiderivative of the function they gave us, and then use the point 0, -2 to solve for the value of c. Those are generally going to be our two steps. So if f prime of x is e to the x plus, so this 20 over 1 plus x squared, I'm going to change into 20 times 1 over 1 plus x squared, because this I recognize as the derivative of arctan. So its antiderivative is arctan, and I'm just going to have the 20 come down with it. So my general antiderivative would be e to the x, because e to the x's derivative is e to the x. And then I'll have plus 20 arctan of x plus c. And again, you can always double check by taking the derivative of what you've chosen, and then the derivative should be the function that you started with. Okay, so this was the general antiderivative. Now we're going to plug in x equals 0, y equals -2, so that we can solve for what c needs to be. Because this one has arctan in it, it tends to be a little extra intimidating, but we're only plugging in 0, so it's not too bad. All right, so f of 0 should be -2, so -2 is the output, and I'll plug in 0 for all of the x values. And c is the only unknown here, so we can solve for it. E to the 0 is 1. The arctan of 0 is saying what angle has a tangent of 0, and that'll come out to 0 because that's where the sign is 0. So we have 20 times 0, which is just 0. If I subtract 1 from both sides, I get that c is -3. All right, so I'm going to go back to this answer and say this formula, but where the c value is -3. So my final answer is f of x equals e to the x plus 20 arctan. Oop, I can squeeze it in. And then we'll say plus -3 or just -3. That's the final answer. So this is the one function that meets both of these criteria. All right, let's try one more. I'm going to write the problem out. I encourage you to pause the video and try it before you watch my solution. See if we can move this down so that sunshine spot is less in our way. There we go. All right, so one more example. Let's say f prime of x is x squared plus 1. And we're told that f of 3 equals 0. Find a formula for f of x. Pause the video here. All right, I'm going to solve it. I'm going to use these same two steps. So find the general antiderivative and then use the point to solve for the value of the constant. So first, the antiderivative of x squared plus 1. I'll use my opposite power rule here. So I get 1/3 x cubed. 1's derivative, or sorry, antiderivative is x, because the derivative of x is 1. And then we have our plus c. All right, so that's the first step. Now I'll put this information in here to solve for c. So I'm going to put 3 in for the x's and 0 as the output. Three cubed is 3 times 3 times 3, so 9 times 3 is 27. (27 / 3 is 9. 9 plus 3 is 12, so c is -12. All right, so our last step here is to come back to this antiderivative formula and just put -12 in the c position. So my final answer is 1/3 x cubed plus x minus 12. All right, so for the last couple minutes of this video, I just want to make a comment about linear motion. I have a little bit pre-set up on the next page here. So linear motion is going to be one of the types of examples that we do for differential equations. So when you're doing these problems, it's still just the same idea as the last two examples we just did. But there's like a little more vocab swimming around. So for motion, when we say linear motion, it's just kind of the scenario where the particle is moving along a line. But it's really just our position application. So if f is position, its derivative is velocity, and the second derivative is acceleration. So let's take a peek at what a problem like this would look like. It looks a lot different for sure than the last two, but it's the same idea and the same methods. The particle moves in a straight line, has acceleration 6t plus 4, initial velocity is this, initial displacement is this, find the position function. So they're using fancy notation, but we can apply what we know from up here down here. So when they say acceleration, they're telling you this is the second derivative. Velocity is the first derivative. And then initial displacement s, that's your f. So they're using the fancy terminology, but these three are connected in that way. So we're going to start with the acceleration formula because that's the only formula we actually have. And then these two pieces of information are helping us just solve for the value of c. All right, so if we know that the second derivative is 6t plus 4, we can go backwards one step. So that's, they're calling it acceleration and velocity. We can go back one step using anti-differentiation to get essentially the formula for velocity. So I have 6 times, so t to the 1 would be 1/2t squared, and then 4t plus c. 6 times 1/2 is 3. Clean that up a little bit. Remember, we're very new to anti-differentiating. So you may find yourself really questioning these steps because they feel awkward because we're doing everything differently. So you might pause here and double check, is the derivative of this function 6t plus 4? If it is, then you're definitely good. If it's not, then you can pause and tweak what you've done. You'll find yourself sometimes using derivative rules by accident. And this is the part where you would just fix that. Okay, so f prime has this format. We have the plus c because we're not sure what its constant would be. Now we're going to go grab the point on this function and say, oh, well, they told us that if I plug in 0 to this, I should get -6. So I'm going to do the differential equations thing and say, all right, well, -6 is supposed to go with 0. So I can solve for C, which is clearly just -6. So my velocity formula, which you can call V of t, but I'll keep that F prime notation. It's 3t squared plus 4t minus 6. So we weren't asked for velocity, we were asked for position. So we're just going to repeat this process one more time. And we have one more point left to help us get the final constant. So if we go one more step to just regular F of t, that would be position. This is what they're calling S of t up there. We have 3 times, so t squared's antiderivative is 1/3 t cubed. And we have 4 times t to the 1's antiderivative is 1/2 t squared, and then minus 6t plus. So C technically already got used. You could do C1 and C2, or you could do like a capital D just to say like they're not necessarily the same number. Again, I'll clean up my constants. 3 times a third cancels out, 4 times a half is 2. So we get position is t cubed plus 2t squared minus 6t plus this mystery value. And now we'll come back up here and say, well, you said the initial position at 0 should be 9. So if I plug in 0 to this function, I should get 9 as the output. Plugging in 0 is particularly convenient here. We can see right away that D should be 9. So our final answer for the position function, which again, I'm calling F of t, but you can call it S of t to match the question, will be t cubed plus 2t squared minus 6t and then plus 9 in that spot. And that's my final answer. All right, so one last comment about the linear motion problems. So it's possible that you're going to see a linear motion problem where in the setup, they don't tell you the acceleration formula. They just say like, oh, it was thrown up in the air, so it's like falling. This object is just kind of falling. So the reason that they don't need to give you a formula for the acceleration in those problems is because if gravity is the only force on this thing, meaning like it's just a falling object, then we actually know its acceleration. So if it is just under the force of gravity, falling object, gravity determines the acceleration, we would know that your second derivative formula, the one that we started with right here, is either, make sure I get my units right here, negative 9.8 if you're in meters per second squared, or if you're in feet per second squared, it would be negative 32. So you'll see in the PCA for tomorrow's class, for Wednesday, you're going to walk through this example and then see another one with it that actually has you default to these numbers based on the units, but then the rest of the problem is exactly the same. It's just these numbers would take the place of this formula that got us started.